This is lecture 2 of unit 1, quantum mechanics. Lecture 2 deals with Planck's law and properties of photon. To recollect back, in lecture 1 we have studied about black body and the spectrum of a black body. It is seen that classical mechanics could not explain the spectrum of a black body radiation. But it was Planck's law which could explain the spectrum of a black body. So, we shall first study what is this Planck's law. Max Planck in 1900 introduced the quantum theory of radiation to explain the distribution of energy in the spectrum of a black body radiation, that is, frequency distribution of thermal radiation. He assumed that the atoms of the walls of the black body behave like small harmonic oscillators, each having a characteristic frequency of vibration. What were the assumptions made by Planck? The first one is that an oscillating atom can absorb or re-emit energy in discrete units. The indivisible discrete unit of energy is h nu and is called energy quantum E. So the formula we arrive at is E is equal to h nu, where h is the Planck's constant and nu is the frequency of radiation. Secondly, the energy of the oscillator is quantized. It can have only certain discrete values of energy E with subscript n, or En is equal to nh nu, where n can take values 1, 2, 3, so on. Suppose you substitute n is equal to 1. So what do you get? E1 is equal to 1 h nu. Likewise, when n is equal to 2, we get E2 is equal to 2 h nu. So and so forth, you'll be getting the value of E3, E4, E5. So it means that energy values are not continuous, but they are discrete. Now, what does Planck's hypothesis state? The hypothesis that radiant energy is absorbed or emitted in a discontinuous manner and in the form of quanta is known as Planck's quantum hypothesis. So this part you got to clearly understand. On the slide, you can see E1, E2, E3, E4, the various discrete values of energies. There is no energy level present between E1 and E2 or between E2 and E3. If you want to understand this with respect to an atom, when radiations falls on an atom, the electrons will absorb energy and go to different higher energy states. So from the ground state, they may go to different levels like E2 or E3 or E4. It depends upon the amount of energy they absorb. And when they come down, they give out the difference in energy values. For example, if the electron jumps down from E4 to E1, the energy value given out is E4 minus E1, which is equal to h into within brackets nu4 minus nu1, where nu1 is the frequency of energy state E1 and nu4 is the frequency of energy state E4. This picture on your slide will help you to understand the basic difference between continuous energy levels and discrete energy levels. It's very important to understand this difference because the entire quantum mechanics is based upon discrete energy levels and not continuous energy levels. The figure A shows a ramp wherein all values are possible. Whereas figure B shows you a flight of staircase. The first step, second step, third step, which has got a parallelism between the discrete values of energy. So if you picturize this in your mind, you can very clearly understand the difference between continuous and discrete. Henceforth, in all our discussion, we'll be extensively using Planck's law, which deals with discrete values of energy. Now, in Planck's law, the equation is E is equal to h nu, that is quanta. The quanta are made up of photons. So we shall understand what are the properties of these photons. The energy of the photon, as we have already seen, is E is equal to h nu, where h is the Planck's constant and nu is the frequency. The velocity of a photon. Photons travel with the velocity of light. What about the rest mass? Photons can never be at rest. So we can assume that the rest mass of a photon is zero. Photons do have relativistic mass. From Einstein's equation, we have E is equal to mc square, or m is equal to E by c square. What is the expression for E? The expression for E is h nu. So m is equal to h nu by c square. So all photons have got a relativistic mass. When do you talk about relativistic mass? When particles move very close to the velocity of light or with the velocity of light, we talk about relativistic mass. And since photons move with the velocity of light, they have got relativistic mass. What about the linear momentum? The linear momentum of a photon is given by the equation P is equal to h by lambda. P is the linear momentum, h is the Planck's constant, and lambda is the wavelength. What is another formula for P? General formula for P is mass into velocity. Since photons move with the velocity of light, in case of photon, momentum P is equal to m into c. So we can say m into c is equal to h by lambda. What about the electrical charge? You got to understand that photons are electrically neutral and cannot be influenced by electric and magnetic fields. Likewise, photons cannot ionize matter. What do you understand by this statement? They cannot ionize matter. When photons, say, are passed through a gaseous substance, the atoms cannot be split into their ions. So photons do not have the property to ionize matter. So these are some of the general properties of photons. To give you a gist of what we have studied in lecture 2, we have seen what is Planck's law and properties of photons. What was the importance of Planck's law? It states that energy is given out in packets known as quanta, and that quanta is made up of photons. And it should be very clear that energy is not continuous, but it is discrete. And we have also seen what are the various properties of these photons. The next lecture, we can see something about what is photoelectric effect.